So we've been running the Visualize These competition for 2 years now. So 2016 started, then 2017. And the competition goals are actually very simple. So what we want to do is we want to advertise the popular open source three-dimensional visualization tools, and then let researchers know about this. So traditionally, these tools include ParaView and Visit. So these are the packages that we already advertise a lot, and we teach, we train them, so various webinars and workshops. And these packages are very, very powerful, as you will see today. They will allow you to do a lot of different types of visualizations. But there are also various other tools, Python libraries and toolkits, C++ libraries, and also domain-specific tools. So anything open source, you can use in this competition. So the goal is to advertise these tools and to let everybody know about the range of possibilities. And also the second goal is to crowdsource solutions to complex visualization problems. So we want to find new innovative visualization techniques and advertise them to all Canadian researchers. That's why in these showcase submissions, we're asking not only for the final visualization, but also for the workflow. So for example, a Python script or a state file or a C++ code or something. But want to make sure that well, first of all, we can reproduce a workflow, and then we can actually pass it to other researchers as well. So in this webinar, we're going to show you the most interesting techniques the most innovative techniques from this year's submissions. A couple of words about the statistics of this year's visualization challenge. So we had 88 participants, or people who expressed interest in submitting their visualization, and the vast majority of them were first-time participants, so they did not participate in the previous year competition. About 80% of participants were students and postdocs, as expected. So normally you would not expect faculty to spend a lot of time on somebody else's visualization. And we had a wide representation from across the country, so not only Westgrid, but also Ontario, Quebec, and Maritime provinces, and from various disciplines as well. We were really surprised by the quality of submissions this year, really, really strong visualizations. And also unexpected, all submissions were done with ParaView, which was interesting. So special thanks go to Dell EMC and Intel for providing the prizes, because without the prizes, we will not be able to recognize and reward the time and effort that our top contestants put into their submissions. And also, of course, will not be able to have the same quality of submissions without the prizes. So thanks, Dell EMC and Intel. And also, I would like to thank Artem Karabenko, faculty from the University of Calgary, who provided the data set for this year's challenge. And as you probably know, it's a simulation, it's a time-dependent simulation of airflow around counter-rotating wind turbines. But because the data set is so large, we actually took only a single time step, just a single time step snapshot, and used it for this year's visualization competition. So the competition results were announced in early December, in mid-December, and it took us some time to go through all submissions. So the first place was won by Jano van der Kalk from the University of Ottawa, postdoctoral researcher. The second place went to Nadia Moiseva, a grad student from UBC. And the third place went to Thangam Natarajan and Dan McDonald and the rest of the team. So it's a joint team from the University of Toronto and the Akkad University. Okay, let's jump to the top visualizations, to the winners visualizations. And so what I'm going to do now is I will spend a few minutes going over the main features of Jano's submission, and then I will pass the microphone to Jano in a few minutes, and he'll be able to provide you more technical details. So we selected these for the first, this visualization won the first prize simply because we were really, really impressed by the quality of the presentation overall. It's a multi-part visualization, and each part contains an informative voiceover providing details on various features in the visualization and also how these details relate to the efficiency of windmills. So clearly, Jano has done quite a lot of extra research on the efficiency of windmills. And the first part is a toy conceptual three-dimensional animation of rotating blades. And what is really interesting here is that you can see it on the left here, that it was done entirely in ParaView. So that is quite surprising because ParaView is a scientific visualization. but not an animation tool. So normally you would do these kind of visualizations in Blender or some other ray tracing packages, but you can also do it in ParaView as well. So what's interesting here is there are multiple elements you can see in this visualization: grass patches, house walls, roof tiles. So because all of these elements are repeated more than once, they are implemented as programmable sources in ParaView, and Jana will give you more details. They output either BTK unstructured grid or BTK polygonal data, and then on top of that, you assign some texture, so that is set to a corresponding PNG image. And then the door, the building door, and the window appear only once, and for these, you can simply just call a plain source, and then again use the corresponding PNG image for the texture. You can also see shadows here. So the shadows behind the house, under the turbine blades, under the arrow, actually implemented with Osprey. So Osprey is one of the options, one of the rendering modules in ParaView. So it's an optional module that usually is included by default, but to enable it, you have to say ray tracing. It's not rasterization. And to enable it, you have to go to the properties of whatever object you're currently visualizing, and enable in the properties somewhere at the bottom. You have to enable the Osprey checkbox and optionally the shadows checkbox as well. And once this is done, and you place the light source nicely, then you can see nice shadows behind your objects. So this animation fades into the next scientific visualization here, where you see the in a cross-section, horizontal cross-section, you see the velocity distribution for the air. And what is really interesting here, the nice selection of the color scheme that shows clearly the air that is slower than the incoming air and the air that is faster than the incoming air. So you can easily differentiate between the two, so looking at the red or blue regions. Next, you have the three-dimensional visualization of streamlines that are colored by the air speed. And then you have a visualization of the isosurfaces of the Q criterion. So that shows turbulence, so basically vorticity and turbulence near the blades. So these are the forces, the regions where the blades actually get pushed. And then the final scientific visualization in this entry is the pressure on the actual surfaces of the blades that clearly shows the regions where you exert pressure on the blades. So I'm going to pass the microphone to Jano now, and he's going to take maybe 5-10 minutes, and then he'll give you more details on his visualization.
All right. Yeah, thank you, Alex. I'll just share my monitor. Yeah, there we go. Okay. So yeah, I thought it was very important to make an intro to actually show the data that is being visualized. So I wanted to put the windmills in their natural environment. So to do that, I introduced objects in my simulation, such as the grassy surface and the house. And as Alex said, I used programmable sources for that, and then applied textures to that. And they also animated the windmills as they would rotate as real windmills. So to show that, I'm first going to show you how I created the programmable sources. So this is ParaView. And on the sources, you can find the programmable source right here. And when you add that, you can choose your output data. So for this one, I use an unstructured grid. But if you look at the documentation for VTK, you can find information about all the other ones. And then below, you can make a script that builds that structure. So the first thing you need to do is actually allocate memory for the output. And the output is defined automatically by ParaView. Then you need to define the points that your polygons will connect to later. So I want 8 points here, and then I set the coordinate for the points. And those points correspond to the points you see here and the ends of the squares. And then the next thing is I also want to use textures. And to use textures with programmable sources, you have to make texture coordinates, which tell you how to map the texture to the polygons you'll define later. So that's a float array that contains tuples with 2 components. So these are 2D components that correspond to your texture. So I do that here. The index here, 0, corresponds to the first point that I defined here. And then you have the texture coordinates 0, 0, which correspond to the lower left corner of the texture, and 1, 1 to the upper right corner of the texture. And for the other 4 points, I only go to 0.5 in texture coordinates, which means I will only use a quarter of the texture. So you can actually select which part of the texture you want. And then you add that, and you set that as the texture coordinates. And one thing I noticed is that you actually need to set the name to texture coordinates, otherwise it doesn't really work that well. I'm not sure why that is, but don't forget to set the name to texture coordinates. And then the final step is to insert actual polygons. So I used quads, which are just simple squares. So for each corner of the quad, I set it to one of the points that was defined first. So for the 0th ID, I use the 0th point, the first, the second, etc. And then I insert that. So that's the one you see here at the bottom. And then I do it again for the next 4 points, which is the one you see here at the top. So I set this to texture coordinates, so you can see that this point is 0, 0, and here you have 1, 1, and in the top plane you only go to 0.5. So then I set this to solid color, and they turn completely gray. And then you need to click this gear symbol to toggle the advanced properties. Otherwise, you won't get the option to load textures. Then you scroll down to miscellaneous, which is here. And you see the field texture, which is currently set to none. So then you click load. And it allows you to choose an image file. So if I choose the intro picture I use for my slides, then they get applied to the textures. So the bottom one was from 0, 0 to 1, 1, so you get the full texture. And the top one was from 0 to 0.5, so you get only a quarter of the texture. And it actually applies it to both sides of the polygons. So that way I could create custom shapes with custom textures. And then I actually use that to build a house and also the cross surface. So here are my programmable sources. And I have the script where I built a large number of quads, and I give the texture coordinates, and then I load the grass texture for it. So that's the grass you see here at the bottom. And I do the same for the house and the roof of the house. And as Alex said, I used normal planes to make the door and the window. So that's how I got a nice environment to put my windmills in. And the next step is to actually rotate the windmills. So here's one of the blades, and if I apply a transform filter to that, that allows me to translate or rotate or scale the blades. Obviously, I want to rotate them so they rotate like they would in real life. And to make that animation, you can go to View, Animation View, and then you get this window where you can add effects. So, for instance, for Transform 1, you can choose to change the translate value or the rotate or the scale. And the numbers here correspond to X, Y, and Z. So if I want to rotate around the Z direction, I would use rotate 2. So for instance, here is one of those. If you double click on them, you can set how the value should change. So at time 0, the value is 0. And at the end of the simulation, animation, the value is set to 5,000. So these are actually degrees. So from frame 0 to frame 1074, it will linearly step through all the possible values for the rotation. And that allows me to rotate this blade around the Z-axis. And then I do that for all the other blades as well, of course. And also I can change the opacity for the 3D error. So in the beginning it goes from 1 to 1, so it's visible, and then it goes from 1 to 0, so it disappears slowly, and then it just stays off. And of course, where is it? You can change the camera path. And all these effects, they change as you play the animation. So that's a bit hard to see in a webcast, perhaps, but if I press play, you'll see that the blades will rotate and the camera will rotate. And so this allows you to make a really nice animation of that. But you'll also notice that this looks kind of ugly, especially the grass surface is very pixelated. And that's because I have not enabled the ray tracing yet. And you can find that all the way at the bottom. There is enable OSP ray, which turns on the ray tracing, and it also allows you to have shadows. These numbers here affect the quality of your render. The higher you set them generally, the better your image will be, but also the longer it will take to generate. I won't do it live because it takes quite a while, but you can see what it looks like, the difference when Osprey is off. I'll have to wait a bit for it to load, I guess. Well, my desktop froze, but if you can still see the slides, on the left you can see.
Slides, yeah.
Okay. Oh, there it is. It took a while to update. Yeah, so here you can clearly see the difference between having ray tracing enabled and disabled. So you can see the shadows here on the right, and the grass is much prettier now, as well as the house. And that's mainly the things that I use to make my simulation stand out. And I created different animations for all the different parts of the data. And in the end, I put them together. And for that, I used a program called KDE Live, which is a video editor that's available for Linux and Windows and Mac. And it allows you to put in all the visualizations you created, put them in order, and make smooth transitions, and also provide narration and background music. So the program, it looks like this. In the left, you can add all the clips. So you just click here, and you can choose all your animations. And then it's simply a matter of dragging them to the video tracks. And you can overlap them like that. And then you can add transitions, such as dissolve, which is what I use to smoothly go from one scene to the other. And it will render that live in the project manager here. So if I press play, it smoothly will transition from one scene to the other. And I use that a lot in my final presentation. And just as simple, you can add the music. So you add that here. You can drag it to the audio track. You can drag it multiple times, so it just keeps repeating. And also here you can easily add effects such as a fade in, so it starts from 0 volume to full volume. And it's a really nice program to do that. And you have another audio track where you can put in all the narration and you can align it perfectly so it matches the actual animation. And yeah, that's how I built my visualization. That's all I would like to say about this at this time. So thank you.
Okay. All right. So next we have, let me forward 2 slides, and I will go to the slide with the second place winner is who's Nadia Moiseva from UBC. She's a PhD student, and she produced this multi-part visualization with 5 separate animations. And each animation is using really impressive techniques. So I'm going to spend a little bit more time on 2 of them, so number 1 and number 2 here, and I will list the rest briefly. And then after I describe all of these details, then if you have questions, you can ask. And Nadia is also in this webinar, and she'll be able to answer your questions. Okay, so the first visualization is what I will call dynamic streamlines with a vertical swipe. And basically what Nadia did here is she drew a horizontal cross-section, and in that cross-section you have a 2-dimensional grid of points, and she used these grid as seed points for drawing streamlines. and then she varied the position, animated the position of the horizontal cross-section, basically forcing the streamlines to be redrawn at each height. And why is this nice? Well, this simply, well, you can view the animation yourself in the website that I mentioned, where we have all visualizations. But this is actually useful because if you have a steady state flow or a single time step, there's no time dependency in the data, you can actually make it look like it's a dynamic visualization, as if you really had some time evolution, even though you don't have it in the data. So it just produces a very nice effect. So that's number one. Number two is animation of a wind flow deformation with integration time counters. So I'm going to, in a few minutes, I'm going to spend more time showing you the details of how this is done. So you can see it actually right here in the middle image. And then Nadia also made several other visualizations, so volumetric plots of regions of high and low pressure around the blades, and also of vorticity. So here in this slide, you can see the volumetric plots of vorticity in the left two images, so this one and the zoom in the middle. And basically what is shown here is isosurfaces of the, sorry, not isosurfaces, it's actually, it might be isosurfaces, I can't remember, of the Q criterion, which is the vorticity. And then the final animation actually combines 11 timelines, so 11 properties that are varying at the same time. And this forms a very nice visualization towards the end of her submission. So it uses several rotational and displacement motions, and just an overall very, very nice movie if you have time to watch it. So also I want to note very smooth transitions between all 5 animations, and by that I mean when any part comes to a close, then all the same elements stay in place, and then they fade nicely into the same positions in the next visualization. So it's just a very nice effect overall. And also she put in some burn captions that provide more information about visualization and about the data set. So I'm going to spend the next few minutes talking about the data, showing you how exactly these effects, some of these effects were achieved. So the first one is how to use the stream tracer with custom source filter. So it's one of the ParaView filters, and it's used to animate streamlines in this visualization. So basically, the first thing you do, well, here you load. This is what the pipeline browser in ParaView looks like when you do this visualization. So here on the left, you load all. You load all the elements of the data set. So first of all polygonal data for individual blades, and then the three-dimensional distribution of air velocity, air pressure, and so on, all three-dimensional variables. Then you pass these data through the calculator, and this is important because you only have the components, X, Y, and Z components of the velocity in the data set, and you want to reconstruct the three-dimensional velocity vector, so that's what the calculator does. Then you apply the slice filter to the output of the calculator filter, and then to the output of slice, you apply the stream tracer. So, the stream tracer with custom source. So there are a number of various stream tracer or streamline filters in ParaView. You want to use the stream tracer with custom source because that allows you to use another part of the data set as the source of seed points. So for input, when you apply this filter, for input you use the three-dimensional data. That's the airflow, air velocity. And for seed source, you use the slice where you have this horizontal two-dimensional grid. And then you bring up the animation view, so go to View Animation, and you animate the slice position from top to bottom. And when you play it back, it produces this very nice animation. Okay. So the next animation is actually something that I've never seen before, and this is really, really impressive. You have these two-dimensional grids of points that are moving to one side, and then they get deformed, reflecting the three-dimensional air velocity, and really fantastic overall effect. So interesting that one other visualization in the Visualize This challenge, so that did not make it to the top 3 visualizations, also use a similar effect to show the velocity vectors moving along streamlines. But anyway, so here's how you do that. You start with stream tracer lines, however drawn. It doesn't really matter how they're drawn. So in this case, they're actually drawn with it. So you draw a horizontal, a vertical plane. I'm getting echo from somebody, so if somebody can, thank you, mute themselves. So you draw a vertical plane through the streamlines. You draw a vertical plane through a data set, and then you use that as a source of streamlines. So to understand how to do these time integral integration contours, you have to understand how these streamlines are drawn in the first place. So what you do is start with a two-dimensional grid of seed points, and then you start integrating from each seed point either in the direction of the flow or in the opposite direction, and that forms a streamline. So the time integration, the time step for integration is constant for all points, for all streamlines. But when you start integrating, basically take the you take point along each streamline, and you calculate. Well, you take a look at the velocity there. You multiply the velocity by the time step, and that gives you the length of advection of that point along each streamline. So, and then eventually forms the streamlines. But when you draw the isosurfaces of constant time integration, time integration isosurfaces, that will actually produce these deformed isosurfaces that will get deformed more and more depending on how non-uniform your three-dimensional air velocity is. So basically what you do is you start with streamlines, and you apply a contour filter to the output of the stream tracer filter. And there it's important to specify integration, so contour by integration time. So contour by integration time. And then you probe the values, the range of integration times that work best for the animation. So for example, what you can do before you produce animation, you can actually bring up a single contour filter, select contour by integration time, and then play with surfaces. So in this case, I'm showing two surfaces at integration time of 1.5 and 3. And that produces these two grids, so separated in by some amount in space, and just a very nice overall effect. And then if you want to animate these planes, you actually, so unfortunately, for animation you have to have, so for each moving plane you have to have a separate contour filter, because when you animate the contour filter, it produces just a single plane, so single moving grid of points. So you animate the view, you animate the contour, and by the isosurface. So you click on the plus button here to create a timeline, and then you double click on the timeline to actually edit its properties, like the time from and to, and the values of the time that you're integrating from and to. And so you do that for each contour that you create, and then that produces a very nice animation. So in the final animation, this is what the timeline, this is what the animation view looks like for Nadia's visualization. And here she's animating 11 properties at the same time, so she has 11 timelines. So a timeline is this white bar here. If you double click on it, it will give you the properties that you can adjust. And basically, you see that she's animating the position of individual contours. So I think they have, she has 9 contours here. And then she also has a variable wind tracer. So its opacity is changing from 0 to 0.2. So it's first it was invisible, and then it's becoming semi-transparent, and then invisible again. So time is on the horizontal axis, right? And all of these properties are playing back at the same time. And then you just go to File, Save Animation, and then it saves you, asks you how exactly you want to save animation, what compression you want to use, resolution, and so on. And then at the end, you have a very nice animation. So I'm going to pause here, and if you have any questions about this particular visualization or to Nadia, then you can ask them now. And if Nadia can unmute herself, and she can actually try to answer these questions via audio, if her audio works.
Hi, good morning.
Excellent. Good morning. Yeah. So if there are any questions, please ask them now. Okay, then let's continue. So you'll be able to ask questions also at the end of this webinar. So the third place was won by a joint team from U of T and UNACAD. So Thangam Natarajan, Dan McDonald, who's actually here in the webinar, and others. And what they did was actually really, really unusual, because instead of displaying the visualization in ParaView or in Visit, or as you usually do and creating a movie, they created the visualization, so basically the isosurfaces and the streamlines that you see here in ParaView, and then they exported them as a 3D scene into Blender, which is a popular ray tracing animation package. And they improved the 3D model aesthetics, so basically made them look nicer in Blender, and they imported all the data into the Blender 3D game engine. And the output is a mock application where you load the data, and then you just walk around the scene, and you can look in different directions. You can zoom in, zoom out. You can toggle the visibility of different elements. like you see, the difference between the left image here and the right image here. And also, so that's one thing, is that you view final visualization inside the game engine. And the second unusual feature of their submission is that they use sonification. So you can optionally run the Super Collider synthesizer audio server to produce on-the-fly audio from the value of vorticity under the microphone. So you can see here the microphone. They can place anywhere in the volume. And then if you're running this Super Collider server at the same time, so the Blender game engine actually passes information to the Super Collider server that produces audio, the intensity of which reflects the amount of vorticity under the microphone, which is actually nice. If you have, if you have a very crowded visualization, and this just provides another channel for displaying, or I guess, hearing information. So I saw that Dan is here in the webinar. If you want to say a couple of words, it's up to you. If you want to say a couple of words about your visualization or show some slides or anything you might have, you can do that now.
Fantastic. Yeah, we have a brief little Tangam and I are here to ask questions, and we have a quick little slideshow to play along. Okay. So as you described earlier, what we were trying to do was acknowledge that data visualization can sometimes be visually overwhelming. And so we wanted to augment the visualization by allowing the user to visually concentrate on one field and listen to another. And as you said, we used the Blender game engine to allow interactivity and sonified the data using Super Collider. So I have a quick little description of our method, the visualization of how we use things. First, we use ParaView to post-process the data. And if you have anything to say about that.
So basically, we set up the scene, if you will, in ParaView. So how we wanted to look, and the different computed data was done in ParaView first. And then we basically exported the X3D files back to Blender. And then with Blender, you can modify the materials and improve the lighting and the aesthetics, basically. And then
similarly, kind of setting up the scene to be realistic and using ray tracing ideas. We had used more the Blender's other engines rather than game engine before, so we were trying to kind of reach that level of more realistic visualization, but the game engine was a little bit limited and heavy as it was, so we were coming up against some of those shortcomings. And so something that I've been doing before was using sound to present data, particularly through ParaView's Python shell, using the sound communication protocol OSC and a higher level wrapper called SC 0.3.1. So basically, I have the data formatted in an array such that every point within our visualization has a local Q criterion value. And I've designed a synth, which I'll just kind of highlight up next, to take that Q criterion value and then produce a sound based on that to the user. So in a little more detail, we were using X3D files from Blender, creating the game environment, and sonifying Q. So the basic idea, even though this is a visualization competition, we decided to try sound to see how it would work, and I guess it resulted in some good stuff. The basics for the sound design was using brown noise as the base sound that you would be manipulating, and then modulating a low-pass filter on top of that. So if you can see on the screen, there's this base cutoff sound, and when you open and close the filter quickly, it creates that windy, turbulent-like sound. So when the Q criterion value is low, we have the cutoff set low, and the modulation depth is proportionally very small. And then in areas of high Q, the filter offset is moved further over and with higher modulation. And so as a result, combining the Blender app and the sound, we allowed the user to toggle visibility of all these flow qualities, being the entire Q criterion range, thresholded Q, as well as streamlines and pressure variables. And and reduce the visual overload of the presentation by using sound. Some of the shortcomings, kind of as we said, were designing user navigation controls. We don't have much experience with that. We hadn't really used the Blender game engine before, so it was a learning experience that we very much benefited from. And the resulting Blender app is very heavy, so we would want to look into probably web-based apps based on similar paradigms if we were to do this again. And I think that's it for now. Thank you.
Thank you.
All right, so if there are no questions to Dan, then I just have the summary. So thanks to all who submitted their entries. So we actually had more than 3 visualizations, and obviously a lot of you have put quite a lot of effort and time into your visualization. So as I mentioned, all submissions were using ParaView for rendering, but you can do similar renderings with a similar amount of effort in Visit as well. And so all animations that you saw today, they could be done both in the GUI and by Python scripting. So doing them in the GUI is a little bit easier, but Python scripting actually gives you a little bit more flexibility and power. And you can also run Python scripts remotely. So if you find that you have large data sets and you want to visualize them, well, you can actually run Python scripts as, let's say, batch jobs on a cluster. And that way you can do it in parallel, and then you can speed up your rendering times. So if you want details for a specific visualization technique that you saw today, then let me know, and I'll send you a simplified version of some of the scripts and workflows you saw today. And finally, we are looking for a data set for next year's, well, this 2018 fall competition. We have some ideas, but if you want to see some data set, or if you want to have your data set featured in this competition, then let me know, and I'll be very happy to talk to you. So on that note, I will stop and open the floor for questions. So once again, you can always send us an email, either email to me personally or support@computercanada.ca, and we'll be happy to answer all your visualization-related questions. So thanks everybody, and especially thank you to all presenters today, Dan and Jano, and Thangam and Nadia for joining the webinar and making presentations and answering questions.